Hello, everyone, and welcome to another insightful masterclass brought to you today by the George Washington University School of Engineering and Applied Sciences. I can see quite a few number of students who have started trickling in for this masterclass today. If this is also going to serve as a quick sound and video check for me, if you can let us know in the comment section which city are you dialing in from. We are really keen on knowing which city or all of you wonderful students joining us from today, which part of the world. So we have Arif from Mumbai. Hi, Arif. Thank you so much for joining in. Okay, another person from Mumbai. We have Bruce from Ghana, Deepa from Bangalore, Sharan from Bangalore, people from Kathmandu, Vijayawada, uh, someone else from Ghana. So yes, we have people joining us not only from India, but some of the folks from Africa, and I'm sure anyone else who is joining in from any other country apart from India or Africa, please drop your location in the comment section. And once again, a very warm welcome to all of you. I am going to wait a little bit more for a couple of more of you to join in before we get started. Okay. So, yes, while the numbers are trickling in, we have a very, very, very exciting and insightful masterclass, like I mentioned, which is brought to you directly from Washington by the George Washington University School of Engineering and Applied Sciences. We are going to do a deep dive into the exciting world, the future of AI. Now, a lot of you, I'm sure in the audience, are very keen to know a lot more about AI, are using AI in some form or the other. So, yes, hold on, stay tuned till the end of the session. It is going to be very inspired. The topic for today's discussion is brain inspired hardware technologies for artificial intelligence, something which is very new, very upcoming, and a lot more to talk about. Thank you, all of you who joined in. I can see that we have crossed 100 participants. So, while all of you are trickling in, without further ado, I am going to start by doing a quick round of introduction to the panel. I would like to start with myself. My name is Sabahat Herzog. I am a senior manager with Seed Global Education. We are a UK headquartered company which facilitates interactions, very insightful interactions like the one today between prospective students like yourself and global universities like GWCs, which is here with us today, and allows you a chance to interact with some of the esteemed faculty that they have, get to know a lot more about their programs, about the institute, the options that you have as a student, helping you in making well-informed career choices about your higher education. Joining me today on the panel is Dr. Adam, who is an assistant professor with the Electrical and Computer Engineering Department at GWCs. Her group works on the development of emerging non-volatile memory devices and novel hardware foundations that will enable new ways of neuro-inspired computing. Thank you so much for joining us today. We also have with us Erin, who's the Senior Associate Director for Graduate Recruitment and Admissions. She has been managing international and higher education for the past 10 years. She's your go-to person, and she is going to be talking a lot more about the programs and the facilities that George Washington University has to offer. So I would request everyone in the audience to please stay tuned till the end, get to know a lot more about the world of AI and what it holds, and also understand in detail about what GWCs has to offer. Of course, all of you attendees for this session are eligible for exclusive application fee waivers and exciting scholarships. So stay tuned. And without further ado, I would now request Dr. Adam to get started with her presentation.
Great. Good morning, good afternoon, good evening, wherever you are in the world. I'm actually in Boston right now, traveling for a conference. Wow. So really, really nice to see all of you from all over the world. I'm originally from Romania, so that's Europe. And right now, let me share my screen. I hope everybody can see the screen.
Yes, we can.
Okay. Welcome. So I'm an assistant professor at George Washington University. I joined the university in November of 2018, and it has been an amazing few years to build my group to develop brain-inspired hardware technologies for artificial intelligence. So I want to start with a question for you. Why do we need new types of computing hardware? That's the question that I hope to provide an answer for you by the end of this presentation. Have you used ChatGPT? We have ChatGPT. So why do we need new types of computing hardware? If you can take just 1 second, I'd be very curious to see how many of you have already used ChatGPT. I'll give you a few more seconds. I know almost all of my students in my classes have used ChatGPT, so curious to see how many in the audience here. Okay, so the answers are in. 89% of you have used ChatGPT. Almost 90% of you have used ChatGPT. That's fantastic, right? This is a technology that's only a few years old, and already we see a lot of adoption of this technology all over the world. We have amazing software. We have seen an unparalleled growth in AI algorithms. While this has been in use now for, let me just hide this. While we have been seeing this in use in the past few years, this technology of artificial intelligence has been actually under consideration and development for many decades. Starting in the early 60s with these very simple, brain-inspired algorithms called perceptrons, where we have layers of neurons interconnected by synaptic weights. But the progress was very slow until the early 2000s, where we had a breakthrough with the convolutional neural networks. We have these convolutional layers capable of extracting features from data. And from that point on, we see an unparalleled growth. Every 3.4 months, we see a doubling in the size of these networks. And we have now this GPT family, this transformer family of systems, and it's going to go still higher up and a growth from there. But the challenge is that we need with this growth of models, we have very, very large size of models. With billions and billions of trainable parameters, we need a lot of data to train this. But we are also requiring a lot of resources to support these algorithms. Just to train the last version, just the last version of ChatGPT's grandfather, called GPT-3, it took the carbon emissions that 5 cars emit in their lifetimes. And this system needed to have a very large number of processors, hundreds of thousands of processors and thousands of GPUs in order to support in hardware this software development. Okay, we see this unparalleled growth in the software side. So let's take a look at the hardware. And my question for you is, do you know what a transistor is? I'm curious how many of you know what a transistor is. So let's have another quick poll. That's what we study in nanoelectronics in the class I'm teaching this semester. So I'm sure not all of you are from electrical and computer engineering. I know everybody here is from different fields of engineering and sciences, but I'm curious to see how many people know what the transistor is. Okay, 80% of you, 79% of you know what a transistor is. That's amazing. Really good. Still less than ChatGPT usage, but very, very impressive. So what is the transistor? I'm not working on transistors, but I wanted to emphasize what the transistor is in terms of importance for computing. The transistor is at the basis of our communications and computing technologies. And the growth, an amazing growth in this technology in the past 75 years, from the 50s when we had the first integrated transistor, and the 60s when we started to have transistor-based circuits, to now where we have billions of transistors in our own pockets, in phones, in laptops, in all sorts of technologies. So transistors are the backbone of the hardware we have for computing. That's amazing. We have seen this amazing growth in transistor development, in transistor integration, and we have been able to have miniaturization of computers and higher performance of computers because we have had this development in hardware. However, we're seeing the progress slowing down for existing computing hardware because in the mid-2000s, we have hit some limits in how much we can scale this. And this is also plotted in logarithmic scale, the same way the AI plot was. So we see that instead of going even, higher slope like the AI, now we have seen flattening of a lot of the core parameters that we would want to see growth in. So while the AI software is rising exponentially, the hardware needed to support it is not doing the same, it's slowing down the progress in that area. So this is not good news for the hardware that we need to support the AI software. The current cost for AI is therefore unsustainable because we need so much hardware to support the software. We need very large amounts of processors, GPUs, that are put together in these server farms. And these server farms are sometimes have to be built next to nuclear power plants in order to support the megawatts of power that is needed to make these server farm run and being able to cool them down. So we need new innovations in hardware to support this astounding growth in software. And to do that, we need to be able to scale the efficiency of this hardware. And where better to look for than biological systems, because our own brain is 8 to 9 orders of magnitude better in terms of power efficiency than the current digital computation. So can we move past this efficiency wall in digital, in transistor-based systems and approach the biological inspired analog-based systems? So the grand challenge that my group is working on and our field as a whole is working on is to build artificial hardware that can achieve the complexity and efficiency of these biological counterparts. And the brain is amazing in its complexity. Of course, we're astounded by what the human brain can do with its billions of neurons and trillions of synapses. And you have probably just eaten dinner and just you're here interacting, answering poll questions, listening, and you're only consuming a few watts of power while doing that. And the human brain is something that we strive to understand better in, of course, brain-inspired computing, but in neuroscience as well. And its complexity is something that, well, it will probably take us a very, very long time to unravel all of the secrets of brain computation, human brain computation. But even smaller brains, like the fruit fly or the mouse, are astounding, because with a few nanowatts of power, we can still see these insects, for example, like the fruit fly, being able to perform an astounding amount of computation and adaptation in the world. So how can we get inspiration from these different brains to develop new types of computing? And my group in particular is interested in two types of inspiration from the brain: drawing inspiration from the diversity of neurons. And this is a list of the different types of neurons that are present in the rodent hippocampus, a particular region deep in the brain that is responsible for learning and memory, as well as the synaptic behavior and variabilities, the synapses being the connections between neurons. And the fact that we see that synapses in our own brain and across different types of brains have a broad range of behaviors, but also variability. The synapses are actually quite unreliable, and yet our brain performs reliable computation. How does it do that? That's a question that neuroscience hopefully is going to answer, and for us to also try to tackle that from the perspective of our own hardware. So there's a true opportunity here to draw inspiration from these neuroscience insights and develop new types of artificial intelligence algorithms that are mappable to new types of hardware that are brain inspired or neuromorphic, we call them. So what are some of these existing neuromorphic chips that have been developed in the past decade or so? And I want to give here a few examples, starting with IBM's True North, that has roughly 1 million artificial neurons and around 100 million artificial synapses, and only consumes a few milliwatts of power. However, it's important to point out that these artificial neurons and artificial synapses are only very rough representations of what our biological neurons and synapses can do, and technology is developed based on a digital, fully transistor-based system. And this chip has several billion transistors already being built in a fairly small node. So there's not a lot of growing for this chip to do. And other efforts, for example, Intel has put together a similar chip, and Spinnaker, this is a European initiative, and I wanted to show here the chip put together in a board with 48 of these cores, and they have built an entire system based on that with 1 million of these cores capable of emulating 1 billion neurons. And the results are impressive. We get similar accuracies in mapping a cortical microcircuit model on this system. But as you can see here, we need to have cooling for the system because once we start putting together a very large system with billions of such artificial neurons, we start to consume kilowatts of power. So if we were to compare a synaptic event, we're still very orders of magnitude difference between what we achieve now in the hardware versus the same or similar event in the brain. So there's a lot of work still to be done. And that's where new types of device technologies come in. By adding these new types of device technologies, such as memristors, we are hopeful to be able to see reduced orders of magnitude, reduced energy consumption for similar tasks. So my question for you is, how many of you know what a memristor is? Let's have another poll. Very curious about this. Give it a few more seconds. Okay. Okay, 22% of you know what a memristor is. By comparison with 80% who know what a transistor is. So hopefully in a few years from now, once this technology hopefully becomes widely available and commercially accessible, you'll also know what a memristor is at the same level. But you're here in this talk, so I'm going to explain very briefly what a memristor is and what my group is doing to advance this topic. So a memristor is a two-terminal device. It has a simple structure by comparison with a transistor that has three terminals. And the memristor in its structure is simple. It has an oxide layer or sandwiches of oxide layers between a top and a bottom electrode. However, don't let the simple structure fool you, because its behavior can be actually quite complicated. It has a physics based on a filament that's very small at the order of nanoscale. And this filament can be modulated, can be changed by applying voltages or currents. And the physics driving this filamentary behavior is not yet fully understood, but we see very useful behavior of this filament conduction. So this filament can be programmed for the device to change its resistance state, and we can have the device have two states, on and off, and switching between them. Or we can have devices performing in a more analog way, where we have an on-off and a lot of intermediate states that are available. So we see this device, an example is shown here in this picture, that we can have learning because we can change this filament and therefore program its resistance. But also, once we remove the applied voltage or current, we are going to retain the shape of this filament. And that's an intrinsic property of the device, and it provides memory. So we have the capability for learning by programming it, and capability for memory by storing the state. And these are the two core behaviors of a synapse. So I wanted to briefly show you this animation of the synaptic inspiration of the memristor device, showing how a synapse is the connection between two neurons in the brain. And this connection strengthens as the neurons fire together. And similarly, we can have a memristor synapse that can change a state and strengthen a state by the firing of artificial neurons on chip. So how do we make these devices? At GW, we work with transistor chips that we procure from foundry, and we add on these memristor devices on top. And the reason for that is because the artificial neurons are implemented in transistor technology, and the artificial synapses are implemented in these memristor devices. And then we add the first layer for the bottom electrode, and then we add the oxide layer and the top electrode, and then we add the contacts to make connections of the synapses to the transistors on the bottom. And you can see here a schematic of how the complete structure looks like. And we have these devices making contact with the transistors on the bottom via using vias. And this is an actual memristor device fabricated in our facility. I'll show you some more pictures in just a second. And of my students actually working on this, and a video for that. So let's get started with the video. I hope. So for this, let me, you see my students here working on the design of different circuits. And we have our facility here. Maybe reduce the music. And this is our facility with my student and I working on the integration of these devices on the chip. This is a partnership that we have in collaboration with the National Institute of Science and Technology and with some companies as well as with other universities in the light of the US CHIPS Act. And the goal for this is to design new types of chips for the US to stay competitive in this arena and at the forefront of computing technologies. So once we have fabricated these devices, we measure them. And I wanted to show here some examples of the behavior that we can observe in these devices that are similar with synaptic devices in different layers of the brain. So you see here similarity with the neocortex synapses and with different GABAergic synapses from the hippocampus. So this is really promising in mapping these devices to actual behaviors in the brain. And based on that, we can build networks like spiking neural networks to perform useful computations such as coincidence detection. So we can see that when we are triggering with spiking inputs particular rows in these arrays of memristor devices, at each point we have a memristor device, we see the a particular pattern being recognized. And when we move to another row, we see a different pattern being recognized. But these arrays are very small. And right now we're working on the integration of a larger amount of devices across the entire stack, from devices, add-on memristors with transistors and building the entire circuitry around it. Plus the software stack to be able to access all of this system by an end user at the top level of the stack. And you can see here the hardware prototype, the photos that I mentioned with my PhD student Imtiaz in the clean room working on the integration on this chip. This chip has 20,000 memristor devices. And you can see here a picture of this device. We can build a variety of different device designs here, device sizes. And then this chip is packaged and put together in this custom board that we call the daffodil board. And this board connects with an FPGA board. And we have a variety of different boards for different systems. And my PhD student, Osama Yusuf, is working at the top level of the stack to support the integration. And this is a collaboration between our group at George Washington University together with Western Digital, with the National Institute of Science and Technology, and with Google to make this system openly available to the research community for measuring these sort of devices and benchmarking algorithms based on them. But we see a challenge. When we measure these devices, we see that no two memristors are alike, and we have a lot of variability in these devices. So in the last few minutes here, I want to give you a brief overview of the projects that we currently have ongoing on how we tackle this variability challenge. On one side, at one end of the spectrum, we're working on better materials and devices, and my PhD student, Shweta, is working on new types of materials, such as high entropy oxides, with intrinsic material constraints to be able to control this filament to take reversible paths, similar to ionic channels in a biological synapse, with the goal of having this low variability memristor devices. And at the other end of the stack, in terms of algorithms that are robust to the synaptic variability that's also there in the brain, I have two PhD students, Joey and Theo, working on different types of networks that have neuronal diversity. And you see here some examples. Instead of just having a network only with pyramidal neurons. These pyramidal neurons are in a specific region of the hippocampus. We are introducing other types of neurons as well, such as basket neurons or axonic neurons that are inspired with similar spiking as we see in the hippocampus. And these networks that have this diversity, for example, the axonic, performs with higher accuracies on the same task by comparison with the network that has no diversity, shown here with purple for the diversity one and with green for the pure pyramidal network. So by adding neuronal diversity, we see increased accuracies, which gives us hope that we are going to be able to translate this into more robust hardware and also provide increased efficiency. I wanted to showcase also our ongoing capacity building. We have an amazing investment in facilities, a new building, our science and engineering hall, with new equipment to be installed in 2024 in our nanofabrication and imaging center, which is in basement 2 level of this facility, which is located in downtown Washington, D.C., 10 minutes walking from the White House. So I'm still astounded that we are able to have a nanofabrication facility so close to the White House. And we're also working on investments in the next generation of workforce in semiconductor, with a broad range of outreach events to high school students, community college students, and a lot of undergraduate students are working in research in our group and in our school. So really excited to be able to have this ongoing capacity building. This is my group at the George Washington University with students, PhD students. Some of them I showed you their work here. as well as master students, undergraduate students. Sometimes I also have high school students helping us. And I want to thank all of my students for their hard work in making this all possible, our collaborators from different institutions and our funding agencies for their support. And I want to conclude with a summary of why we need new types of computing hardware. Is because we have to support the exponential growth of large AI models with new types of devices, new types of circuits, and new types of systems. And Memristors are promising as artificial synapses, but we need to be able to scale up and have prototyping across the entire stack, from devices all the way to architectures and applications. And a big challenge for this is the fact that we have non-idealities, we have variabilities, and we're working on solutions to be able to engineer better devices in our nanofabrication facility, but we also need algorithmic approaches to be able to support hardware implemented with devices that are less than ideal. So we need a software-hardware co-design with inspiration from neuroscience. With this, I would like to end with a question for you. Would you like to learn more about such next-generation technologies at GW? And while we get the answers there, I want to thank you all for your attention. And if you have any questions, please put them in the chat. We will take the questions in the Q&A section. Thank you all so much.
Thank you. Thank you so much, Dr. Adam, for your insightful presentation and sharing all of those lovely details with us. As you can see, we have the poll results in front of us. 96% of the attendees do want to know a lot more. So we are going to dive right into it. There are quite a lot of questions which have come in. I would request everyone in the audience to stay tuned. We will be taking those questions shortly. I would now like to hand over to Erin, who would explain more in detail about the various programs and offerings at GWCs.
Thank you so much. Can you see my presentation okay?
Yes, yes.
Perfect. Okay, that's a really tough presentation to follow. It was quite interesting, and I hope you'll stick around just a little bit longer. I'll take no more than 10 minutes just to tell you a bit about studying at GW and the programs that we offer and the facilities that we offer our students. And then we will take your questions, as our host mentioned. And I've seen some amazing questions coming in, 95% of which I cannot answer. So Dr. Adam will be happy to answer more questions, and we're so happy that you're very interested in this topic. So one thing I always mention when I'm talking to students about considering a graduate program and a graduate program in the US is, there are a lot of different factors to consider. There are more than 2,000 universities across the US alone that you could choose to study at. So it's important to ask the right questions when you're searching for a university, when you're searching for the right opportunity for you. I'll try to tell you answer these questions about GW, about our School of Engineering for you. If I don't, please feel free to put them in the chat if you have other questions. But the important thing is, at the end of the day, we want our program to be a good fit for you, and we want you to be a good fit for our program. And hopefully we'll find that that we are, in fact, a great match. So a little bit more about GW in general. As Dr. Adam mentioned, we're located in Washington, D.C., in the nation's capital. We're a city campus. We do have 3 campuses, as you can see, but anyone studying in the programs we are talking about today will be studying at our main campus in downtown Washington. Another thing that's unique about GW is that of our 25,000 students, approximately 15,000 of those are graduate students, meaning we have more graduate level students than undergraduate students. And that really speaks to an emphasis that we have on graduate level education, programs, resources, opportunities. And I think that you would see that clearly yourself as a student here. In the School of Engineering and Applied Science, we have 6 academic departments, one of which, of course, is the Electrical and Computer Engineering Department, where Dr. Adam works, and then 11 fields of study, more than 90 tenure and tenure-track faculty members, and 22 million in research spending. And that number is, I think, a year old at this point, and I think has gone up a fair bit since then as well. Again, just a number that indicates the amount of resource and focus that our faculty have in bringing in those research dollars and developing new technologies and trickling down those opportunities to our students. Dr. Adam talked a lot about our Science and Engineering Hall, and you got to see it in those videos, which was great. So I won't spend much time on this, but this is our home at GW. This is where most of our faculty offices are. A lot of our research is conducted, our admissions and advising offices, our career offices. So this is sort of a hub of learning and of administration for our students. It's a really cool building. It's one of the largest teaching facilities in Washington, D.C., and it has a lot of really interesting technologies going on there. So here is a list of the MS programs that we offer at GW in the School of Engineering and Applied Science. Of course, computer engineering and electrical engineering being among the opportunities that we offer. And then additionally, here are the PhD programs that are offered in our school. Of course, within these PhDs, a lot of different areas of focus and areas of research that you could explore and potentially engage in. Now, I know we've already received some questions about scholarships and funding. This is a really common question as students try to learn and understand the process of studying in the U.S. and what it takes to get there and start a program in one of our universities. So at our master's level, we offer merit-based scholarships to our applicants based on the competitiveness of the applicant and the applicant pool for that semester. These scholarships can range from 25 to 75% of the tuition cost, and you're considered automatically if you've completed an application to our programs. The only opportunity that I can mention now that you do need to do a little bit extra to apply to is the SEED scholarship, and I'll let my colleague Sabahat talk a little bit more about that, or maybe put some information in the chat about that. But this is a really cool opportunity. Yeah, perfect. Thank you. This is a really cool opportunity for students who have joined us here today to apply for extra consideration for our scholarship opportunities. Please work with SEED directly to apply, and we want to see a lot of great applications for that as well. Doctoral funding works a bit differently than MS funding. And if you're admitted to a PhD program, in most cases, I would say 80 to 90% of admitted students at the PhD level are also receiving a funding package with their admission. And that could include full tuition coverage, as well as a living stipend in exchange for possibly teaching or research assistantship responsibilities. Just a few more notes from me, and then we'll take the many questions that have been coming in. So please continue to put questions in the Q&A link if there are things that we aren't addressing yet for you here. I just want to mention our Career Services Center. This is an important piece when you're deciding to attend a university in the US. You're really investing in not only the education that you'll get there, but the network that you'll get there, the career services, the all the resources that are available to students. So our Career Services Center is located right in the Science and Engineering Hall and works explicitly with engineering students and a lot of international students. So they're very well versed in helping you prepare for a job search that might be across the US, around the world. You may be looking for internships during your program. You may be looking for full-time career opportunities after your program. Our Career Center is there to support you throughout your time from your first day as a student. Two more quick slides from me, and then I'll hand it off. So another thing that is good to think about when you're considering U.S. universities is what is the advantage of the university that you're considering. So I think it's pretty clear from the presentation that you've seen today that our research capabilities and our technology is one of the huge advantages, as well as the quality of our faculty members here at GW at the School of Engineering and Applied Science. Another advantage is the personal attention that our students get in our academic departments. So most of our departments offer small to medium class sizes with faculty who are leading researchers in their areas and can really build relationships with students, help you explore your own interests, and help make sure that your skill sets are ready for the career path that you've chosen. We also have a lot of connections with employers for internships, for research opportunities, for careers across organizations like Microsoft, Amazon, Facebook, now Meta, the US government for US students, contractors like Raytheon and Leidos. So you'll find tons of opportunities and a really strong network of students when you come to our institution. Speaking of our current students, here are just a few of our current students who are available to chat if you have some questions about the student experience. So Dr. Adam can tell you things from a faculty perspective, I can tell you things from a staff perspective, but sometimes you may also want to hear directly from current students in a program. We offer this chat on our website. The website's linked here. These are our graduate ambassadors, and you can send them a message, an inquiry about their experience in a certain program, about living in Washington, D.C., whatever the case may be, and they are happy to respond to you. That's all from me. I'll gladly turn it back over to our host for moderating some questions. I do want to offer anyone that joined us here today an application fee waiver. So if you've decided that GW may be a great fit for you, we'll be happy to receive your application. Our next deadline is January 15th, and you can apply with the fee waiver listed here, SEED NOV for November, NOV 23. And we'll be happy to waive that application fee for you. Our website is here, which includes a lot of the information that I talked about today and more. And the email address, engineering@gwu.edu, where we can help address any questions that you have. One more quick plug for my team. If you go to the website mentioned here and follow the Learn More links to info sessions, we are offering info sessions for every department in the coming weeks, including with department faculty presenting about the programs and the curriculum for that program. It'd be a great opportunity to learn more about studying in GW, and Dr. Adam herself will be presenting for the ECE department. So we hope that you'll join us. I believe that one is on December 6th, but please check out the upcoming sessions on our website and get registered, and we hope to talk to you again there. Okay, I turn it over to Sabahat for questions.
Thank you. Thank you so much, Erin, for sharing all of that information. I have put the application fee waiver codes and the link for the SEED scholarship where the students can go and check. In case if you have any other information which you would also like to share with them, feel free to drop it in the chat window. I can see there are a lot of questions which have come in, and given the time that we're at, we're going to try and take on as many as we can. I would like to start with one question which has been repeating itself. Dr. Adam, this one's for you. A lot of people in the questions want to know whether they can get a spot in your research group or how can they be a part of your team. So yeah, that is a burning question, as I can see, that has come up from Andrew, the Rahman, couple of other people. Yes, so
I'm
think
very happy to hear that. I'm always looking for hardworking and motivated students with a passion for AI hardware. So if you are interested, please apply to our master's and or PhD programs. I work with master students on their theses, and we have the capability of doing that. The thesis, the master thesis is for 1 year, but some students joined me in their first year as well, with the second year of the master working on research on the thesis. And also PhD programs are typically 4 to 5 years. And I saw a question about direct entry. We do offer direct entry PhDs as well as entry after a master's. So I will be putting some links in the chat to help the students, as well as I saw some questions regarding the courses. And I will be putting some links in the chat as well. We do have courses on this. Of course, we have the research, so we have to have the courses as well to support our students. We have courses on machine intelligence, on reinforcement learning, courses on hardware implementation of neural networks, and these are graduate level courses. Our level is 6,000 for graduate programs. And also what's very nice about our graduate programs is that we have the flexibility of allowing students to take courses from other departments and sometimes even other schools. So it's really a flexible curriculum from that perspective. And I will be putting the bulletin link there so the students can take a look at the course descriptions themselves.
Thank you. Thank you so much, Dr. Adam. I think that that answers the second most asked question. So I think we've covered those. I would like to take my next question for Erin very quickly. Erin, we have shared the application fee waiver. A quick question from someone in the audience. They want to know till when is this valid? Is it only applicable for the fall 2024 applicants, or how would this application fee waiver work?
Oh, great question. And it would be applicable for the following spring as well. So we typically recommend that students use the fee waiver within 1 calendar year of receiving it. So you could use this from now through next fall, simply because a lot of the information could change after a year, and we would encourage you to join another session to learn more. Just a reminder again, as I mentioned before, that if you're thinking about applying to our upcoming intake, that will be for fall 2024. Applications are rolling in now. They're open for you at any time, and our deadline is January 15th.
Thank you. Thank you so much, Erin. Erin, another quick question for you from the audience. Nikita here has said that the minimum requirement for the data analytics program for TOEFL is 100, and she has scored a 99. So she wants to know, is she still eligible for apply, and should she go ahead and put in her application for GWCs?
Yes, this is a tricky question because some of the minimums and some of the requirements are flexible and some aren't. I know as a student, it's hard to understand what might be flexible. In this case, I can speak to that program and say that we do usually consider students who have missed the mark by just a few points. So yes, we would encourage you to go ahead and apply. Just please know that students who are below the 100 mark on TOEFL, I think it's 130 Duolingo and 7.0 on IELTS. They do take an English course in the first semester to make sure that your English it's called English for academic purposes, so that you're prepared to write and conduct academic work in the English language. If you're in India, or I know we had a number of students joining us from Ghana today as well, I'm sure your English is already excellent. But yeah, those are the requirements. I will say in general to keep in mind, especially if you're considering applying for a PhD, some of the funding, the scores will be stricter for. So for example, like some of our teaching assistantship opportunities, for example, you really have to meet the English requirements of 100 on TOEFL or the other scores that I mentioned to be able to teach in a program. So there are some places, especially with regards to funding, that those scores might be more important.
Great. Thank you. Thank you so much, Erin. I hope that answers quite a few questions from everyone in the audience. My next question would be for Dr. Adams. So Norbert wants question is for Dr. Adams, and they want to know is how effective and useful is neuromorphic computing over AI?
So that's an excellent question. Right now, neuromorphic computing is still in the early development stages, and we are working on making this technology useful in order to be able to map these AI algorithms and provide solutions that are much more energy efficient. but we don't yet have the commercial reach. We are still working on this technology. Hopefully in 10 years, 20 years, the situation will be different. What I envision is a system where we'll have heterogeneous technologies. We'll have existing processors, we'll have existing graphic cards, but we'll also have additional accelerators based on neuromorphic computing or other types of accelerators for different tasks. So it will be supporting task-specific tasks with specific hardware.
Thank you. Thank you so much, Dr. Adam. I hope that answers your question. The next question, Erin, is for you. And quite a few students in the Q&A have asked about the GRE requirements. So can you speak a little bit more about the test requirements for the various master's programs at GWCs?
Yes, thank you for that question. GRE is currently required for PhD applicants and optional for MS applicants. So for MS, if you've taken the exam, you feel like your scores are strong and will help you in the application process, then yes, please submit them to us. But it's optional and it doesn't hurt you if you don't submit those scores for MS applicants. For PhD, the GRE is currently required. It does need to be submitted also by the deadline of January 15th. If you have a question also about whether or not English proficiency scores are required, we do have a list of exempt countries on our website. And you can check it is based on your country of education, not your citizenship. So some universities do that differently. For us, it's based on the country that you earned your prior degrees in, and you can view on our website whether or not it is required based on that country.
Great, thank you. Thank you so much, Erin.
I just want to add that I added the link in the chats for the master's and PhD requirements.
Oh, thank you.
Yeah.
Thank you. Thank you so much, Dr. Adam, for that. Dr. Adam, the next question is for you. And a few students have asked it, so I'm going to try and club it all together. Is what scope of careers, or what are the different type of careers that students can look into if they were to study further and go further into the field?
Yes, well, I am biased for electrical and computer engineering. I personally have chosen it because it provides an amazing flexibility. A lot of different technologies are incorporating innovations in electrical and computer engineering. And I wanted to highlight that we do welcome applicants from other fields. So if they have a background in another type of engineering or another type of science, we welcome those applicants into our department, and we appreciate their diverse backgrounds. So these sort of careers that students who are graduating in electrical and computer engineering can get are from, of course, working in making new types of devices. For example, at Intel as process engineer or device engineer, or at Apple as circuit designer, or at Google as a hardware developer using FPGAs. And we see a lot of interest in traditional software companies such as Google in expanding into hardware because they understand the need for software hardware co-design. So in our department, we're very keen on providing both the hardware skills and the software skills to support the students if they want to go for a career more in the hardware side or in the software side. And we have graduates who are software developers, as well as the software hardware co-integration. So it's really very flexible from that perspective. And we have other faculty working on cybersecurity, different types of secure hardware, networks, power, and smart grids. So it's really, really broad.
Thank you. Thank you so much, Dr. Adam. I'm sure all of you in the audience can see there are quite a few links which have come into the chat window, both from Erin and Dr. Adam. please make note of all of these links, save them somewhere. They are going to be really helpful for you to get the information that you want. Erin, my next question is for you, from a few students who want to know, does GWCs accept the 3-year undergrad degree for their masters and other programs?
3-year degrees from India are typically not accepted, unfortunately, for entering our master's program. That being said, I would encourage you to email us directly if you have further questions about that. And if you do email us, of course, the email, I'll put it in the chat again, is engineering@gwu.edu. Attach your degree certificate or your mark sheets. We are very familiar with a lot of the universities across India. We spend a lot of time there. And so we can just take a glance at your specific credential to give you a firm answer. But generally speaking, we do not accept the 3-year degree programs.
All right. So thank you for all of you. You can reach out to Erin and she will be happy to help you. I know we have come towards the end of the masterclass, but I am going to stick around for a few more minutes. If that's okay with both of you, I'd take a few more questions. Great. Thank you. So Dr. Adam, this question is from Nathaniel, who says, is there any contribution from neuroimaging in the development of brain-inspired hardware technologies for AI? If yes, what is the extent of such contributions? This is a loaded question, but I will leave it up to you.
Yeah. This is a really fantastic question. We do benefit from a lot of insight in neuroscience, and of course, ways of understanding how the brain works, neuroimaging, different types of ways of measuring brain activity across a large number of neurons, like neuropixel, etc., provide insight into that. And I know there have been advances in building connectomes, so having an understanding of how networks of neurons are happening in the brain and mapping the entire neural network in particular brains. So these sort of insights are very, very helpful. We are, of course, only starting to get some inspiration from that, and we are at the beginning of that. But the inventories that we see in neuroscience, such as hippocampome, is an example of an inventory from neuroscience with the different types of neurons, different types of synapses. These are all from insights in neuroscience, and we use them to get inspiration from our own hardware and software. So yeah, for sure, we have to use all of these insights from neuroscience.
Great. Thank you. Thank you so much, Dr. Adam. I think we have come towards the end of most of our questions. I can see a lot of you have asked a couple of questions still are revolving around admissions, application waivers, the GMAT GRE requirement. We have sort of covered those. So I would request you to refer to all of the links which we put in the chat window so that they can be proved to be more insightful for you, and that should help you in getting an answer to most of your questions. My last question, Dr. Adam, would be for you. Is it okay? Can I go ahead?
Great. Yes, and I will actually make my comment after that as well.
All right, perfect. Yeah. So the last question for this evening is from Henrik, who wants to know how might the unique properties of Memristors, such as non-volatility and adaptability, revolutionize the landscape of both memory storage and neuromorphic computing? And what are the current challenges in fully integrating Memristor-based technologies into practical applications?
Yes, another excellent question. So here I talked about the Memristor application for brain-inspired computing, but of course, Memristors can also be used as a memory technology to replace, for example, the flash drive or the solid-state drives that we have. And in my opinion, I think Memristor technologies, either the ones that we're working on based on our materials or other types of non-volatile memory technologies will be adopted in the future. And there's a lot of industry interest in this. Companies like Intel, IBM, Samsung, Toshiba, Micron, a lot of companies are having programs in this. So we'll definitely see commercial products in this. And I think neuromorphic computing is going to be the driving force more so than memory. But a big challenge for these devices for neuromorphic computing is the variability that I mentioned. No two devices are alike, and the devices also change from cycle to cycle during operation. And if we can address that issue to some extent, it would be very helpful. But also being able to have a high yield of these devices, a lot of the devices that we fabricate to actually work, plus to have the facilities to make these devices together with transistors, and not a lot of commercial foundries already offer that. So there are still a lot of challenges to overcome, both in terms of research and in terms of development for production.
Great, thank you so much. Yes, Dr.
I wanted to make a quick question, because I was looking through the Q&As and I saw some questions regarding the in-person versus remote.
Yes.
And I did want to mention that for research in my group and for our doctoral programs, they are in person, and we're working on experiments, hands-on, building new hardware. So we need to have in-person attendance and involvement in these programs. But I know we have some master's programs that are online, right?
Yes, there are a few master's programs that are online and managed by GW's online engineering school. If you have questions about those programs, please feel free to email us as well, and we can direct you to the right contact. Most of the international students that we hear from are eager to come to the US physically and study here on our campus. So we'll be happy to work with you on what program would be the best fit for you.
Thank you so much. We still have close to 180 students who are in the room. Thank you so much for sticking with us throughout the end of the session. I'm sure you've got a lot of insights, you've got a lot of information. The chat window is still active. You have all of the links present there. You can feel free to reach out to the team at GWCs, or you can connect with us at Seed Global Education, and we will be able to guide you to the team at GWCs. So before we end, firstly, Dr. Adam, thank you so much for joining the panel today and enlightening all of us with all of this remarkable technology and the work that you are doing. Thank you so much. Thank you so much, Erin, also for joining us today and giving us all of this information. Once again, thanks, and I will see you. Bye.
Thanks you so
hosting.
Much.
Bye, everyone.
Thank
Bye.
you. Bye.
Hope to see you at GW.
Yes.